Okay guys, welcome to this online class section in which we are going to introduce a complex number and present the different representation of a complex number. So let's start by talking about so we are going to talk about complex numbers and the different representation of a complex number. Okay, first of all, let's give you a bit about the story of the complex number. So basically, at some point, mathematicians understood that it wasn't possible to solve, for example, the equation x squared plus 1 equal to 0, because it will mean x squared equal to minus 1. And if we assume that x is a real number, there is not a real number whose square can give minus 1. Is that clear? So if I square a real number, I expect to get a positive number. But people says, okay, as there is no real number whose square can give minus 1, let's invent an imaginary number called I, such that I square is equal to minus 1. So there mathematicians invent an imaginary number called I, such that I square, so that number that we invent was called I, so that I square is equal to minus 1. At that point, it means that we were now able to solve the equation x squared plus 1 equal to 0, because the solution was x equal to I or x equal to minus, because if you put, it will give you x squared plus 1 equal to 0, because if minus 1 plus 1 0. Yes or not? So by inventing this number, we has been able to solve this equation. But this number is not a real number, because in real life, if you square numbers, you expect to get, okay, in real algebra, squaring number, you expect to get a positive number. That's why we call it imaginary unit. The imaginary unit. Okay, then from this number, people understood that, okay, maybe it can be interesting to combine real number, so to create new numbers that has a real part and an imaginary part, and they define the so-called complex number. So what is a complex number? A complex number can be defined like this: let A and B belongs to R. Okay, the number Z equal to A plus IB, it's called a complex It's called a complex number. So if example of complex number, 1 plus 2i. In this case, how much is A? A is 1, right? And B is 2. Another complex number, 1 minus I. A will be 1 and B will be minus 1, right? Also, this Z equal to 2i is a complex number, yes or not? With A equal to what? No, A equal to 0 and B equal to 2. But even if I give you Z equal to 3, for example, this 3 can be written like 3 plus 0i. Doubts? Even if I give you Z equal to root 3, to root 3 or root 5, I can write root 3 over like root 3 plus 0i. What does it mean? It means that any real number, it's a complex is a complex number. We write it like this, that we say that the real number are included in the set of complex Is that clear? Any real number is a complex number. Nice. So I hope I convince you that C, the set C, is bigger than the set R, right? Nice. Then, so any real number, any complex number can be written in the form z equal to a plus ib. This forms, so any complex number z can always be written in this way, right? This a is called the real part of z, and we write it like this: the real part of the complex number z. And b, I didn't say I times b, I said b. B is called the imaginary part of z. So I repeat, a is the real part of z, and b is the imaginary part of z. Nice. Then what is the next step? But how can I represent a complex number? When I have my we saw that real number, we can represent them on a line, yes or not? For example, 2, we put it here, 1. But what about if I give you 2 plus 3i? How can you represent it? I hope that some of you know know Gauss, the mathematician. Gauss says that, okay, let's represent a complex number in a b-dimensional plane, okay, where this axis here is the a and this one is the b. Is that clear? This axis is the a and this one is the b. So we have 2 for a and 3 for b, yes or not? So the number will be 2 for a and 1, 2, 3 for b. The meeting position, that will be, so this will be our number, yes or not? This position here, let me put it with, this is the number, this is our z, yes or not? So we saw, and the representation z equal to a plus ib, it's called the algebraic representation. Okay, algebraic representation. Is that clear? So now you understood that we now conclude this video by looking about, are there some alternative representation of a complex number? Instead of representing a complex number with like this, is there any other way to represent a complex number? People invent 2 other ways to represent a complex number, called the trigonometric representation, and the exponential representation. Is that clear? So this is also called the exponential representation, is also called the Euler representation. Is that clear? Because Euler is the mathematician that found it. Now let's first go on the trigonometric representation. So what means a representation? Just means another way to write the same number, okay? We saw that typically complex numbers are given in the algebraic form, so z equal to a plus ib. And there, in this when the complex number is given like this, the representation is a and this is b, right? And it means that the complex numbers stand here. So what do you use to identify the complex number? You use the a and the b, right? But there is a we can also use two alternative information. We can use this distance and this angle. Let me call the distance r and call the angle theta. Tell me, if I give you the angle theta and I give you the distance r, you are able to identify the position of the complex number, yes or not? So you can. This means that we can use a and b, or we can use r and theta. When you use r and theta, this will, by using r and theta, this will lead to what we call the this will be what we call the trigonometric representation. Okay, so when you use r and theta, you are using the trigonometric representation, but a and b is the algebraic. What is the relationship? How can I compute r and theta using a and b? This r is also called the modulus of the complex number. Okay, this r here, the modulus of the complex number is the distance of that complex number from the origin. Yes or not? So how do you compute it? R is nothing, you know the Pythagorean theorem, right? If I apply the Pythagorean theorem, this is b, right? This length here, this one is a, this is b, so we have that r is the square root of a square plus b. And now for theta is called the argument, so this is called the modulus of the complex number. This r is called the modulus, but theta, it's called the argument. The argument. Okay, to find theta, I will not go in details, but anyway, theta, it will be arctangent of b over a. This if a is greater than z. Okay, if you take a number, if you are using a complex number with its a greater than 0, and it will be let me think a bit. It will be arctangent of b over a minus pi. Okay, if a is smaller than z. Okay, these are the formula that you use to compute r and theta. Is that clear? Once you get r and theta, what is the trigonometric representation is given like this. Z will become just r multiplied by the cosine of t plus I sine of t. Is that clear? Because why this? Come on, look from this. How do we get this trigonometric representation? You remember that we said that the algebraic representation, the algebraic representation is z equal to a plus ib, right? You said that I hope you have some notion of trigonometry, because look, this is this angle theta. You can see that the cosine of theta is the adjacent side divided by the hypotenuse, right? Which is r. You know this rule? Cos of theta is the adjacent side, which is a divided by r. So from this you get that a is r cos theta, right? A is r multiplied by cos theta. And for this, in the same way, you get that the sine of theta is b divided by r. So what do you get? You get that at the place of a, you can write a equal to r times the cos of theta plus b, which is, so we have first have I and then we have r sine theta. Yes or not? Now we can take out r. It gives you r multiplied by the cosine of theta plus I sine of theta. This form, this is called the trigonometric form of the complex number. Let's do a couple of examples. Suppose you are given the complex number z equal to 1 plus I. Let's find this is the algebraic form. We need the trigonometric form. To find the trigonometric form, we need to find the r. R means the modulus of z, right? And we saw that it is the root of a square plus, so 1 square plus 1 square, because I remind you that b is not I, but it's the coefficient of I. So the modulus is root 2. Okay? Then, as we know the modulus, now we can find the argument. We saw that theta will be r tan of, now what is b? B is 1, right? Because here is the formula. We will use this one because we will just use the one of r tan because a is greater than, so it will be 1 over 1, because yes or not, equal to r tan of 1, but r tan of 1, I remind you, is pi over 4. Okay, so how do I, z will be, my trigonometric form will be r, which is root 2 multiplied by the cosine of pi over 4 plus the I times the sine of pi over. Okay, doubts? This is called, this will another example for the trigonometric. Let's try to do, for example, the trigonometric form of minus 2i, z equal to minus 2i. We want its trigonometric form. Okay, here a is 0, and b is minus 2, right? Okay, I forget to tell you that for this, as when this you see that you cannot use this formula if this work only when a is not 0. Okay, because you cannot, no, excuse me, it work, never mind, because we can use infinity. Okay, never mind, excuse me, even when b is 0, it's whole. So we have that. Let's go and find, so a is 0, so is that clear? We can use also this formula, the formula we can write here when a is greater or equal to 0. So let's say that theta, r first, will be square root of 0 square plus b here is minus 2, right? That will be 2. This is r. Now theta will just be r tan of b, which is minus 2, over 0, which is, it will give me r tan of minus infinity, right? That is minus pi over, the r tan of minus infinity is minus pi over 2. So we get also theta. So we can write down that our z, the complex number we had at the beginning, is 2 multiplied by the cosine of minus pi over 2 plus I sine of minus pi over 2. And this is the trigonometric form of this complex number. Okay? If the question of my student is which one do we use here, if we know, I say that is this hold for a greater or equal to 0. Yes. Nice. Finally, we will write down the exponential. The exponential form is directly what is the exponential form directly come from the trigonometrical form. Okay, because Euler says, okay, let's define, let's say that exponential of I theta, where theta is an angle, it's always equal to, by definition, to cosine of theta plus I sine of theta. This is a definition. So exponential of I times theta is cosine of theta plus I sine of theta. Example, if I have cosine of pi over 6 plus I sine of pi over 6, this can be written like exponential of I times pi over 6. Is that clear? But please, this happen for theta belonging to R. Okay, for real angles. Doubts? So at the end, what do we get? We get that we get that from the trigonometric. If we are right, if we move the trigonometric representation says that z is r multiplied by the cosine of theta plus I sine of theta, right? The exponential representation will just be z equal to r multiplied by exponent. All this stuff here, let me use a different color. All this stuff here is exponential of I theta, yes or not, by definition. So it will be r times exponential of I theta. So we are saying that the exponential form of any complex number is r multiplied by exponential of I theta. Okay, where this theta is the argument and r is the modulus of the complex number. Is that clear? The example we saw, when we saw 1 plus I remind you that we saw that 1 plus I was root 2 multiplied by sine of pi, cosine of pi over 4 plus I sine of pi over 4, right? This was the trigonometrical representation. The exponential representation of this number will be root 2 then exponential of I pi over 4. Is that clear? Okay. Tomorrow we should see in the next the next lecture we will see talk about operations on complex number, talk about how to compute the n roots of a complex number, and discuss about the polynomials, the degree, the roots of a polynomial in the complex field. Okay, thanks for your attention.